So this morning I actually checked on the React Motion repository, and it has officially crossed 5,000 stars. All right. Thank you. This was open source almost exactly a year ago at this very conference. And I just want to thank all the contributors, all the 44 contributors on the repository, and all the countless number of people actually using it in production. And this is a project I'm very proud of. Thanks. And also, apparently, it's on the mug now. You have a Redux and you have React Motion afterwards. So, you know, guess we made it, right? We made it on the mug. Pretty cool. That just wasted 1 minute. Let's start for real. Today, there's no cool demos. There is no library to present. There is no other nice things I want to, concrete JavaScript code that I want to show you. So today is, instead of that, I want to talk about something that's been very close to my heart. And I've been using JavaScript for a long time. And as a matter of fact, I've started using JavaScript when I didn't even speak English. What I did was, I was literally copy-pasting until the braces, and I was like, this is a relevant snippet of whatever that code is when I was young. And, whoa, this is lagging, but all right. And what I'm trying to say is, when I joined the React team, working alongside React and on React for the last 3 years, I've noticed a lot of phenomenon that doesn't happen normally in the JavaScript community that I want to underline today. Some of them are bad, some of them are good. Some of them you really only get to experience when you talk to the core developers on a daily basis, just like I did, luckily. So I consider myself to be a very fortunate, in that fortunate position. And today I want to share these concepts with you, these concepts that have stuck with me throughout the years and helped me reason about software in general, not just writing a specific library, but writing all libraries. And it has also helped me in other aspects of life, of debating with people over stuff. So I was thinking about a way to make good software engineering decisions, including designing good APIs, just every API possible. And I want to, as a true engineer, I want a reliable way of making good decisions consistently and having more reliable discussions over these kind of software. A little bit of anecdote while we're trying to fix this. This is an anecdote that, I have no idea how to fix, I've been telling my friends. In object-oriented programming, you have this concept of superclass and subclass, right? Everybody knows what object-oriented programming is and superclass is. We all learned that in computer science 101. And have you ever wondered if the subclass, let's say the superclass is A, and the subclass is B, and B has more properties than A, B extends A, why do we call a subclass a subset? Why is it a subclass and not a superclass? Has anybody thought about this? It's a trap question, by the way. There's a very deep answer to that. And the answer is another question. What are you actually counting? I'm just going to start with this thing. It works. So what are you actually counting here? Are you counting the number of methods on a subclass, or are you counting the number of instances? And the answer is you're counting the number of instances, and that's why a superclass is called a superset, because in terms of numbers of instances, it includes in the pool of its own instances all the instances of a subclass, even though it has strictly less properties than a subclass. So you see, if you count the wrong thing in software engineering, you might think we're talking about in the same terms and we're like making the same baseline assumptions, but you're actually talking past each other, and in these kind of pathological cases, you're completely against each other in this sense. Sponsored by Rango.io. I've been talking a lot this year, today, sorry about that. And the slides finally work. On the spectrum of abstraction. So today, you saw these trees pass by, right, flashing by a crossfade. I want to explain a little bit what these trees are. These trees are something that I created myself. In reality, in real life, they are actually graphs, probably directed acyclic graphs. But for the purpose of this talk, we're going to use trees for simplification. At the top level, you have something that's abstract, right? And the abstraction allows you to descend each level and get to the concrete use cases here, which are green leaf nodes, which are your actual products. We're all software engineers. Our ultimate goal is not to create abstraction. Abstraction is the mean for us. For computer scientists, this is the end for them. But for us, it's not a joke. For us, we're trying to aim for the green leaves here. We're trying to aim for the concrete products. And in the context of React, you could say React is that abstraction. And the middle layer abstraction in white here could be something like a React, a plugin in the React ecosystem, for example. And your concrete use cases would be the app that you're actually creating. To start, I wanted to clearly define a few terms so that we don't get these wrong when I use them in this talk. We have the concept of power here. And when I talk about power, it's without any emotional attachment to it. When I mean power, it means the ability to drill down this level of abstraction and get to your concrete use cases. For me, this is power. And when I talk about utility, it's on the other end of the spectrum, and it's attached to concreteness. Right? Something is immediately useful if I don't need to understand how, what abstractions to master to make it work. So a concrete product that you, as a, for example, startup founder, you deliver to your product, it should be preferably devoid of abstraction level to traverse. It's a concrete product, it just works. That's what it means for me in this context, useful. So in this context, we can also say React is not very useful, but without any emotional attachment. But by saying React is not useful, I simply mean that React is not ready as a product yet. It's a product for the engineers to use to actually craft concrete products at the end. And the bad part about software engineering, about life in general, is that if you want to drill down the levels of abstraction, you have a cost, right? It's not free. There's no free cost abstraction. So every time you drill up or down, you pay a cost. And our goal is to be able to cover all the green leaves with the least amount of red circles possible and with the least amount of cost. Can we all agree that this is our goal in general? Okay. It's much easier to work with this way. And so this was the last slide that was passing by. I bet lots of people know what principle of least power is, or for example, the Pareto Principle, which is also very close to this. It basically says, if you want to cover all these concrete use cases, and in this case, of all the leaf nodes, I want to only cover 4, then I probably want to use the least powerful tool possible to achieve them, because there are less mental overhead, right? You pay a little bit of cost in the last circle there, but you also abstract over these two so that you don't have to worry about the 2 concrete use cases at the bottom. And this is important. This is for us. And another example of this is libraries versus framework, the often debated thing. And if you think about libraries versus framework, it's only a specialization of this paradigm where I say libraries are basically me choosing nodes lower in the tree. And frameworks are me choosing nodes higher in the tree where I might cover use cases that you absolutely won't need. But that's okay because someone will need them, and we can all refer as a community to this single tool. And this is what the purpose of a framework is. It's half social and half engineering. And in this library case, for example, I don't need to take the rightmost nodes in the library because as a master of drilling up and down the hierarchy, I already understand that this is not needed for me. So there's a trade-off here. And framework, you can see using very formal principles why this might be easier for newcomers. A set of boilerplates that are just there already. Oh, sorry. And right now, also, we have this problem in the JavaScript community of having people complaining and having too many micromodules. So how would you represent micromodules in this hierarchy? Well, micromodules will literally be your red circles immediately surrounding the green leaf nodes, right? You have all the concrete use cases, you can just npm install any concrete thing without learning even how it works. But the problem is that there are too many of them, and we create a new problem where like the quantity is too much for us. This is another problem. But this essentially, without saying this is bad or not, this is how it's represented. Once it's represented, we can debate all sorts of things with this. This is a quote from me that someone should put on a mug also. Lots of problems in software engineering, lots of the big problems arise from a bad understanding of where we should be in the levels of abstraction. Writing code is easy, to say the least. Writing code, typing on the keyboard is easy. And if you get your abstraction wrong, if you create your library wrong, or if you target your product wrong, no amount of editor refactoring can correct that. You can only have yourself as help. And the consequence of this tree is because every edge has a cost, you can potentially lose a lot of adopters if you're on the wrong level of abstraction. So for example, when you're trying to promote a library or a startup product, or you're a teacher teaching a concept to a student, any concept in any domain, what happens is if you're way too concrete, you end up not covering all the use cases, all the green leaves that your customer or student needs. And this is suboptimal. But if you end up too abstract, what happens is that, especially in the context of a startup, a competitive product, is people have way too much mental overhead trying to understand what you're trying to describe here, and they lose interest at the end too. So ideally, you would circle just the perfect amount, but circling the perfect amount is probably an NP-complete problem, and we need to rely on our intuitions now as human beings. And the other consequence of that is as you go more abstract, and this is a very important point I want you to remember, as you go more abstract, you lose more and more of the situational specific properties. All right? And I want to define property as formally as I did with power and utility in this case. Properties here, for me, in the context of this talk, means the things we want to optimize, maximize as engineers, the unique features you can have when your product is not overly general. So I will give you a very simple example. Let's say we have our programming language, it's JavaScript, all right? But I turn every token in JavaScript into a string. A variable would be a string, an object would be written down as a string, and everything would be a string. Now this would be cool because it's one unifying concept, right? Strings. And there are programming languages that are built around nothing but string manipulation. But what do we lose here? If you try to use a linter, if you try to use a static analyzer, they will all fail because they won't even catch the most basic of your typos, because everything is a string now. It's undistinguishable. Once you have distinguishability in the lower level of abstraction, this is where the sweetness happens. It's when you have these kind of properties that arise from it. It's not like a uniform mass of things. You can actually see this is a function, this is an object, this is an if statement, right? You have different tokens. And now the struggle is to, at which level of uniformity you want. Another application of property is also, for example, Redux. Redux limits your expressivity in a good way by saying no mutability. Immutability. And immutability and mutability, if you put that on the ladder of abstraction, where would they be? Of course, immutability would be higher, right? Because mutability can do strictly more. You can have immutability by simply not mutating, right? But this is not the point here. The point here is to do things as straightforwardly as possible. And in Redux, when we say no mutability, what property do we gain from that? Well, one of the most interesting properties we gain is time traveling, right? Time traveling is a property of immutability. And time traveling has been implemented on top of mutability, but it has been very hard, right? And it's not that popular. So this is the benefit of going to a concrete level to exploit these properties, but not too concrete, because then you end up not covering all the use cases you want. So this is another quote I want you guys to remember. We're often, as software engineers, we seek more power because for us this is appealing. This is where reuse comes from. This is where the elegance comes from. But in practical daily engineering, we're often not seeking for more power. We're seeking for more principled ways of using our existing power. Because if we were seeking more powers, then we would probably have stopped at gotos, right? We have all the powers we need already. We don't need to explore any other concept anymore. With gotos and machine 1 and zeros, we can already do everything. It's all Turing complete anyways. What's the point? The point is to reduce our expressivity in a principled way. So instead of gotos, we now have for loops, right? And nowadays, instead of for loops, we have map filters reduce. And so if you extrapolate that, you can think, we have Redux, which is nice. Redux is a reducer. Can we actually restrain our expressivity even more? And what would that give us? Would that give us something still powerful enough for daily uses? What if instead of a reducer, we have a mapper? What's the property of a mapper that reduce doesn't have? Well, in a mapper, every item is independent of each other, so we can parallelize them. So it gives you very interesting opportunities for visualization and unordered visualization. I won't go into detail what that means, but it's just to simulate your creativity to think about having constraints and the properties that arise from having these constraints. So no, it's not always about look at all the powers I have, look at what possible things I can do. It's about actually having them right now, right here, without any cost of abstraction, and this is very important. I want to present a few case studies, and these are all the products that we use in our everyday engineering in JavaScript. And instead of having these kind of debates and picking situational arguments to say like this library is better because look at its code style or something like that, or look at its performance, I want to talk about a very general way of why a library might be preferable to another one, viewed under the lenses of levels of abstraction as we saw just earlier. And this way you can make sense of things that will come in the future, which is very appealing. First of all is Grunt versus Gulp, right? I don't actually personally have an opinion on this, as I myself, I've stayed on Grunt, because I don't have time to learn all of that. Gulp, but apparently Gulp is the one winning right now. Has anybody wondered why? And yes, you could say in some way it's because it's more idiomatic node, blah, 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 stuff like that. But there are very good reasons why historically these kind of build system always come out as the winners versus declarative DSL that is Grunt. Again, no hard feeling against Grunt. It's just two paradigms. Declarative DSLs work really well when your domain is well defined, and because they're on the levels of abstraction, they are very tightly constrained things. They are almost near your leaf nodes. So when you use the declarative build system and it does what you want, it's very convenient. But once it doesn't do what you want, you have to twist yourself to do what you want it to do, right? And in this case, why is it relevant for a build system? Well, it's because a build system, traditionally, it hasn't been as well defined as, for example, a finite state machine in computer science, where we say, you know, we're done. This is what a state machine is. This is the limit of expressivity of a state machine, and this is the floor of expressivity of state machine. It's not well defined. A build system, if you think about it, a few years ago, it used to handle dependency management, and now it doesn't. It used to handle module bundling, and now it doesn't. And now we have transpilers, and we don't know where to put this transpiling step, so we put it into a build system. And now build system handles all sorts of other tasks now. So the role of a build system is basically to say, everything I don't know where to put yet temporarily, I'm going to put it in the build system as a build step. And this is important. This means that the build system is a moving target. And it means that my green leaves are like this all the time. Years after year, they're like this. And when the green leaves, when the requirements are constantly changing, do you want a declarative DSL, or do you want to step up a level of abstraction and use functions that don't change over time? You want functions. You want functions because they're flexible enough to accommodate to whatever future use case you might have, and you know there are future use cases that you haven't predicted yet. This is why you want to stay at the level of function. And ultimately, if another build system comes up and market itself as a declarative DSL, first thing we are going to notice that if it ever wins temporarily, it's because it's very concise. It doesn't have any, you don't have to learn anything because it's not a function that you have to reason about and master, right? It's just, you put this configuration, it's all in the documentation, and it just works. But ultimately, you will see that you will lack expressivity a few years down the line. I'm not saying which one is better right now. I'm just saying the current situation in JavaScript probably does not favor declarative DSL for build systems. Now, React versus templates. This is the subject I wanted to discuss for a very, very long time, because I've been in the IRC, sitting in the IRC and sitting in Slack and then subsequently Discord for over 3 years now. And every time there's a veteran JavaScripter coming into IRC, one of their questions is always, are you actually putting HTML into my JavaScript? You know, it's like, have I answered this before? Yeah, I did. But they keep asking the question, and we keep giving them the same answer, right? We keep referring them to the same talks, and they come out still, defensive. So today I want to attempt to resolve this once and for all. So if you have such a friend who wonder why we putting HTML in our JavaScript, maybe you should refer them to this talk in this precise minute. What are templates? Templates are data. Templates, even if they have if statement inside them, they are ad hoc if statements, right? Templates, even if they have loop statement inside them, they are read as data by JavaScript, right? They are still data. And our position within the React team is basically saying, data is very nice. Data is much lower in the ladders of abstraction, so it is what you want, ideally. But the situation of the web has changed. JavaScript is used for more than just creating interactive forms. If you only create interactive forms, then yes, probably we should actually go with templates. If you're only writing blog post engines, probably should go with templates. But no, we're actually creating fully fledged applications now, and they're all Turing complete. So maybe, just maybe, we should step up a level of abstraction. And this is a concession. Let me repeat this. This is actually a concession. We're not proud of saying we need an extra level of abstraction to get things done. We're never proud of saying that. But we're saying that because we do need this extra level of expressivity. And so you can see it in the resulting situation where Ember right now with a templating system, they're slightly limited in expressivity, but they get a lot of nice performance benefit out of it. Because they're more concrete, more properties, more optimizable. More fixed situations that you can actually optimize. And the Glimmer engine is a testament to that. And all the other template engine can do that too. And luckily, React is not too far behind, because even though we're a level above and we lose a few properties that Ember can optimize, we can actually coast on decades of actual research on functions and how to, for example, do function lifting and constant inlining as is done by Babel optimization modes right now. So we restore these kind of performances by coasting on existing research, but theoretically we did lose a bit of power here. We did lose a bit of properties here in exchange for power. So it's all about data versus function and which level we should be on. And this is why in the React team we made a concession to use functions and not data. And another interesting property of React is diffing on views and diffing on model. Right? React is definitely the former. You write your functions, and ironically, at this part, we chose to use data because we said now we need a performant diffing algorithm. How do we get performance? Data. Why data? Because data is comparable. Data can be sorted in order. Data can be made distinct, can be made the same. You can imitate, reproduce data. You can discard data, for example. And the virtual DOM is basically based on this assumption that we can do all these sorts of things with data that you can't with functions. If you have learned the theory of computation, you know that function cannot be compared, unfortunately. So what happens is in React land, we diff on the views at the end. We have this neck here that is all database, and we said this is where we're going to do all our optimizations. Whereas in contrast to other frameworks that are accidentally or coincidentally also using templating engines, they diff on the model. Diffing on the model is data, except you have a whole chain of function and computation after the model. You haven't gotten to the view yet. You have still many steps. And these computations, because you cannot compare them, you lose these properties, right? It's not data anymore, so you have to restore these properties somehow. And the solution we found is basically computed properties, where you track each step of your computation to restore these properties. But this is much less convenient. Of course, I'm biased, but I think this is what's actually happening. And without giving another opinion of how this, which one is superior, I think this is the position we are on in terms of React against the other popular frameworks right now. Another one is mutability versus immutability. This is also weird because from someone who has programmed in C, for example, or that come from a mutable first language like most of the mainstream languages, they don't get it. They don't get why immutability is important, because they will always tell you, but I can do strictly more with mutability. So why would I choose something that's less powerful? And what do you tell them, right? You're like, this is true. You can do more. You can write more programs than me using mutability. That is true. But this is not the point, right? And now you can actually give them a concise reply. You can tell them it's not about the potential power of doing more. It's about exploiting the properties that you gain by doing less. And this is why immutability is important right now, because you're doing less of it. You gain this property. Redux, time traveling, for example, nice comparison, should component update, which has become a critical hook in the React lifecycle events. All of that from doing less, not doing more. And now let's extrapolate toward a future topic. JavaScript CSS versus traditional CSS. So there has been one good argument I've heard against inline CSS, against JavaScript, is that giving a layout algorithm the power of a full language is way too much. We lose way too much properties, and this is true. This is undeniably true. Just check the debate of, for example, a grid-based layout or a constraint solver versus Flexbox. And CSS is obviously less powerful and expressive as it currently exists. So theoretically, if we can do everything with CSS, theoretically, right? Implementation is another detail, let's say. But if you can do everything with CSS, definitely try to do things with CSS, because it becomes much easier to reason about, because there's literally not much to reason about anymore, because there's no abstraction level to go up and down to. So theoretically, it's easier to analyze CSS, and I personally have always wanted to see a CSS static analyzer which can analyze the boundary of your components and tell you, for example, if you translate this text into German, it will overflow, something like that. And this kind of properties, it's very hard to get when you have the power of a full Turing-complete language. Unfortunately, we're not doing that, and unfortunately, as shown by preprocessors, we are on the wrong level of expressivity here. We did need functions after all. We can't just use a declarative DSL anymore. And this, for me, is at the heart of the argument of inline CSS, is being able to use a real language so that we can stop twisting ourselves around that DSL. Not because it's just more familiar JavaScript, or we can use the existing bundling infrastructure. Of course, these are all nice practical benefits, but theoretically speaking, it's all about the levels of abstractions here. So a few concrete experiences that I've had over the years. This is the last section. First of all, and this is an obvious one, don't cover every use case. What's the easiest way to gain performance? Do less work. Do less of these use cases. Shave off green nodes if you don't need any. Shave off all the leaf nodes. That's how you gain easy performance. You can gain performance in other ways, but this is one easy way to do it. And this is an obvious advice again, but now we can actually have, and this is the attractive part of thinking in terms of level of abstraction, is that we can have a clear justification to not cover every use case now. Because when you cover every use case, you lose on opportunities of optimization. And I don't mean just speed optimizations. You lose on all the optimizations of mental overhead, of composition, of nicer user experiences, and you don't even know you're missing out. You don't know they exist in the first place. You went way abstract, right? And true to be told, having worked on the React team, I realized that React actually loses out on lots of abstract optimizations because of the API surface that we need to support. So yes, we support a smaller API surface for the nicety of it, for the conciseness of it, but not just for that. We support a smaller API surface area so that we can have ourselves some wiggle room for performance optimizations, for mental overhead optimization, and this is very important. And of course, don't constrain or over-constrain yourself too much so that you don't have any wiggle room left, right? So if you look at the texts that take off, disregarding what you think of these technologies, some of them you might love, some of them you might hate, some of them might seem purer than the others, but the texts that do take off and do become popular, they tend to be averagely powerful technologies. They are not all powerful, and they are not all constraining. There's a reason behind that, and this can be explained if you think a little bit more in terms of abstractions. And the other one is, Sebastian has mentioned this before in another talk called Minimal API Surface, that this part of the talk I think people didn't understand too well, is it's okay to copy-paste code. It's totally okay, and this is a little bit controversial to say because as engineers we want to not do it twice, right? But sometimes, if you think about this very simple tree here, the cost of abstracting things away overweights the benefit of actually having a single node, right? I can either circle 2 circles here or 1 circle. Some people will prefer circling the circle up there, but now you incur the cost of drilling down. And every time I read your function, I need to understand what's actually happening, and this can have exponential effects. So it's okay to sometimes copy paste, but then this again is up to your judgment now. And this is also the phenomenon of NPM micro modules where people say, everything I'm going to write twice, I'm going to abstract it away. And now we have, surprisingly, JS fatigue, and we don't seem to understand why. It's because consistently we're paying more cost to abstract things than to actually use them. Don't be swayed by elegance. And elegance, once again, is a very overloaded term. Sometimes it refers to things that are way too powerful, and we say, wow, this is the single unifying principle. For example, monads, macros. These are so pretty, and we as engineers, we find them very nice because with one single thing, we can tame so many concepts. But you can bet, and if you reason about this in terms of trees of abstraction, you can bet that a single unifying principle is too general to be popular and too general to be used in a more immediately usable way. It takes time to master. Of course, if you're the only person that needs to master it, then it's all up to you. But if you're making a library, writing an app or something, and you are imposing this onto the user, then be aware of what you're trying to do here. You might not be doing enough for the user. You might be leaving user too much levels of abstraction to drill through for the user, him or herself. And when in doubt, use examples. Why do we need to use examples? And now here is a good reason, very rational reason for doing so. We use examples because examples on the tree of abstraction is on the very, very, very lowest level, right? You have your library which abstracts over things, and examples are basically copy-pastable templates. They basically said, instead of understanding the libraries right away, here are your actual values that I can provide you. And if you want, you can understand this later by connecting the dots. And this is why examples are helpful. So when in doubt, and when you're lacking ideas of how to express your libraries correctly, write a README, write a few examples, write more documentation. And this will make things much easier, even if your code or your abstraction is leaking. So, in conclusion, funnily, I can put this talk itself on the levels of abstraction, right? So this talk itself on the levels of abstraction would be extremely abstract, would be very vague, which, ironically, again, by my own definition, is probably the most useless talk of this conference. But now you know that the definition is actually consistent, right? It is also, by my definition, and without any emotional attachment, a very powerful talk in the sense that if you can master the levels of abstraction and drill down these ladders yourself, then you can potentially apply this paradigm, just like I did, to various use cases, to a lot of these concrete use cases, but only if you apply these things. If you don't apply it, if you just bike shed and if you think in theory only about this level of abstractions, then you won't be finding much use for this talk at all. So I urge you to think about all of these. Next time you write a library, next time you write an app, you start something new, try to think in terms of abstractions and where you want to be before starting to actually code and execute. Thank you.